In this lecture, we are going to talk about two different concepts called infinite sequences and series. So infinite sequences and series. So what are they? For example, let's look at this list of numbers. So for example, you can say 1 and then 1/2, 1/3, 1/4, 1/5, like that. So when you write numbers like that, we call this is a sequence. So you separate the numbers by a comma, and then so this is just a list of numbers. And also we can look at this list. So for example, 1 and then 1/2 squared, 1/3 squared, 1/4 squared, like that. So these are what we call sequences. And also, since it goes finite, we call these are infinite sequences. So these are infinite sequences. Infinite sequences. And then the finite sequences. So you're gonna see finite sequences in your computer science classes. So those are like for example, if you get an image, that's a finite sequence of zeros and ones. So if you get an audio file, that you can write as a finite sequence of zeros and ones, because those are finite sequences because there's an end. You know that when the image ends, when the audio ends. But in mathematics, what we're trying to do is we're gonna go to infinity. So so we're gonna consider like in a much like higher class. And then the next thing is what we're trying to do is we're gonna add the numbers. So you can add these numbers. For example, in the first one, we can add 1 and then 1/2, 1/3, 1/4, like that. And also in the second one, you can also add 1, 1/2 squared, 1/3 squared, 1/4 squared, like that. So when you add these numbers like that, we call these are series. When you add the numbers, we call these are series. When you separate them by commas, we call these are sequences. So the second one is what we call a series. So these are infinite series, actually automatically infinite because these terms added up to infinity. So infinite series, infinite series. So but in the future, sometimes we even ignore this term because we consider or most of those sequences are either infinite sequence or infinite series. But now there's a major question. So the question is, sequences are clear, you have those numbers listed, and then what's going to happen when you add the numbers, you get series. But the question is, what's going to happen, because you are adding numbers infinitely. So the question is, what do you get? Actually, you can see that we're going to prove that in the future. In the first series situation, when you have 1, 1/2, 1/3, 1/4, so what's going to happen? These numbers added up to infinity. So you're going to get there's no end. It can go to infinity. It can get larger and larger and larger. But if you look at the second one, you can see that you can prove actually, but we cannot prove it in our class, but is in advanced calculus class you can prove that you're gonna get pi squared over 6 if you add all these numbers. You're gonna get pi squared over 6. It's kind of interesting what's gonna happen. So you can see that it looks like much the same, but in the first one it goes to infinity, in the second one it goes to pi squared over 6. So you can see that the concepts are kind of different. So you need to like carefully see what's really going on, and then this is the idea like we try to understand in this chapter. So so let's try to go to the first one. We're gonna study sequences in this lecture, and then in the future lectures we can talk about series. So so sequences. sequences. So so let's look at the definition. So the definition, a sequence is a list of numbers. If you say ordered list of numbers, it will be much better, but list of numbers is okay. List of numbers a1 comma a2 comma a3, like that, and this is the nth term. So we normally write the nth term, we write the first 2 or 3 terms and put 3 dots, and then write the nth term and then we put 3 dots again. Okay, in a given order. Order matters. Okay, when you have a sequence, the order matters. So a sequence is a list of numbers in a given order. That's what we call a sequence. And we call these are the terms. These are the terms of the sequence. These are the terms of the sequence. These are the terms of the sequence. So we call these are terms of the sequence. A1 is the first term. First term, and an is the nth term. Nth term is the most important one for our calculations. An is the nth term. Nth term. The integer n is called the index. So a1 is the first term, and then an is the nth term, and then the integer n is called the index. Okay. So let's look at a few examples. So what we call the representation. So the first one. So let's say you have numbers 1, 2, 3, like that. This is the nth term. So this is a sequence, infinite sequence. So this is the nth term. So there are several representations. One representation is you just list the numbers like this, 1, 2, 3. Sometimes we even put like a curly braces around it, so you can do that also. And there are other notations as well. So for example, we can just write the nth term. So we can write an equal, what's the nth term? You can see that 1, 2, 3. So the index 1 number is 1, index 2 number. So we try to use the index to write the nth term. So you can write 1 to write the number. So it's just n. See, it's a 1, it's 2, 3. So you can say n term is n. So that's one way to write it, n term. Okay, so this an is what we call the nth term. That's one way to write it. What are other ways to write this? So you can say that your n term is n. So we can say put a curly bracket or the braces, and then we can say, so we put a like nth term and then put a braces around it, and then you're gonna say the starting number and the ending number. What's starting number? Starting number n. You write the index is 1. That's the starting number. So it's like you're writing a sigma notation, n equal 1, and it goes up to infinity. So we can write it like that. Oh, yeah. So this is like, you know, the way to write it. Like we can write it. Oh, If it is really obvious, we sometimes just write like that. But this obvious situation, that means you start with 1 and end with infinity, which we just write it like that. But the best way to write it is, you can say, you can put the numbers in equal 1 and infinity. Let's look at more examples. How about the second one? How about this one? 2, 4, 6, like that. So so in this situation, you can see that. So what are the index? So how it works? In this case, the index is 1, index is 2, right? Index is 3. So what's going to happen? So you can see that your nth number is index times 2, right? When it's 1, it's 2. When it's 2, it's 4. So index times 2. So you can write this one as 2 times the index. So 2n. 2n. So n term is 2n. So you can write it. So it is 2n. That's the nth term. Okay, that's one way to write it. What are other ways to write this as before? So you can write this one as 2n, n going from 1 to infinity. But it's not always 1. That's why we write 1 to infinity. So how about this one? So I'm going to go with like several different examples just to make sure that we understand this one. So let's say 2, 3, 4, like that. That's easy one. So what's the nth term? Nth term, n equal, you can see. So what's the nth term? So there are several ways to write this one. But you can see the index is 1, index is 2, index is 3. So what happened? Every time it is 1 more than the index. So this is n plus 1, because it's always 1 more than the index. So it's n plus 1. That's the nth term. Nth term is n plus 1. Nth term is n plus 1. So let's look at more examples. T. So what about 1/2, 2/3, 3/4, like that. So in this case, you can see that the nth term is n over n plus 1. It is n over n plus 1. So think about the index. So when it is 1, it is 1 over 2. When it is 2, it's a 2 over 3. So like that, that's the n over n plus 1. So you try to use n to write your nth term. Okay, look at the nth index. So if you look at the nth index, so I'm going to write it here. So when the index is n, it is n over n plus 1. So that's how you get it. And then it's going to continue. That's the nth term. Good. And then how about this one? 1/4, negative 2 over 9, 3/16, negative 4 over 25. So you will look at few numbers like that. Okay. So what is the nth term in this situation? So you can see that. Let's look at the index. So what's the index? Index is 1. So when it is 1, it's 1 over. It's not 1. It's like 1 over 2 squared. So right, 1 over 2 squared. So we can write few numbers. So it is 1 over 2 squared. And if you look at here, it is 2 over 3 squared. It is 3 over 4 squared. So now we see the pattern. Okay, so that get the pattern. But also there's a sign change. So how to make the sign change? So what you want to do, you have to multiply by -1, but not every time. You're going to multiply by -1 when it is even. You multiply by -1 when it is even. So that means what you want to do, so it's a -1, but it has to be even number. So that means if it's a 1, you can write 1 minus 1 here, or -1. You can write this one as 2 minus 1 here, like that. So it's a -1, 3 minus 1, like that. So that means your general situation is, you can say an is -1 n minus 1. That's going to give the sign, and your numbers are n over n plus 1 squared, n over n plus 1 squared. Or you can write it using braces. So -1 n minus 1 n over n plus 1 squared. What is the starting value of n? Starting value of n is 1. So 1 to infinity. You can ignore this one when it's obvious. And also you can see that for n minus 1, you can also put n plus 1. It still work. So there are several different cases that can work. Okay. So so I'm going to give you an exercise. So why don't you try this one? So so the problem is, what is this? 3 over 4, -4 over 5, and then 5 over 6, and then -6 over 7, like that. So what is this equal? What is the nth term of this one? So I'm asking, what is the nth term? Okay, that's for you, for practice. Good. Okay. So and then, so let's try to talk about. So there are, like, this is one way to write it. You know, just you can see the sequence, and then you can write other terms, and then what we can do is we can talk about the idea of convergence. So let's talk about the idea of convergence now. So convergence and divergence. Convergence and divergence. Convergence and divergence. So what we mean by converge? So for example, let's try to look at the numbers like this. So what we can do, one way to do is a visual representation. You're gonna like, you know, you're gonna go with index. You're gonna plot the point. Like for example, let's say at 1 you get 1. Let's say at 2 you're gonna get -1/2. So that at 2 you're gonna get -1/2. So yeah, so I'm gonna kind of not put the numbers here. I just put only the value. So it's -1/2. At 3, 1/3. At 4, -1/4. At 5, 1/5. And you can see that the numbers fluctuate. Okay, numbers fluctuate. So if I kind of draw a graph that passing through those numbers, so it looks like this. Go like that, and go like this, go like that. So you can see that those numbers getting closer and closer to 0. You see that every time it gets closer and closer to 0. So that is what we call the idea of convergence. It's getting closer and closer to something. Oh, there's a trend. Okay, there's a trend. There is a trend. The trend is what we call the convergence or the limit trend. So if you see a trend, you call this sequence converge. If there is no trend, we call it diverge. So what do you want to see? You want to see whether there's a trend. You kind of trying to go like to a special value. If there's a special value that it goes, we say the sequence converge. So let's write the definition. So converge. So if an nth term gets, let's start it like that, gets closer to a number L, when n goes to infinity, we say an converges. An converges to L, and write the limit of n goes to infinity of an equal L. So we pretty much, what we're trying to do is just try to find the limit that you learn in Calc 1. So you try to find the limit. If there is a limit, and if this number is a finite number, this is how we normally write it. It's a finite number. So we say that the sequence converges to that L. Okay, converges to L. So we just try to find the limit. So it's just, so if you want to show that a sequence converge, just find the limit. So if that limit is a finite number, we say the sequence converges to that number. Okay, so let's finish the definition. If there is no such number, if there is no such number, we say the sequence diverges. We say the sequence diverges. The sequence diverges. If there's no such number, we say the sequence diverges. So let's look at several cases. So the first one, what we can do, we can look at the graphical representation. It's much easy to understand. So these are my numbers. So it's A1, the first number. When you plug in 1, it is A1. When you plug in 2, this is A2. When you plug in 3, this is A3. So the best way to kind of plot the numbers and see how it behaves. So like that, and you can see that these numbers goes down to 0. You can see that these numbers goes down to 0. So the limit of an when n goes to infinity is 0. That's a finite number. So the sequence converges. It's very clear. Let's look at another example. So you can see the first number is this, the second number is there, third number is here, fourth number is there, like that. You can see the numbers fluctuate. Even though they fluctuate, you can see that they are getting closer and closer to 0 every time. You can see getting closer and closer to the x-axis, So every in every direction is getting closer and closer to the x-axis. Here now it's much closer, so it's getting closer and closer to 0. So you can see that even in this case, so what's going to happen? You can see the limit n goes to infinity. If you call these r a's, in, you can see that still goes to 0. So that means the sequence converges. Let's look at this example. So how about this one? So A1 is 1, and then A2 is negative 1, and then A3 is 1, and then A4 is negative 1. So it's a 1 and negative 1. It's going to fluctuate between 1 and negative 1. You can see that they fluctuate, but there's no trend here. So you cannot see that it's getting closer and closer to a specific number. So you can see that in this case, no, the limit does not exist. So there's no limit because it's just either 1 or negative 1, 1 or negative 1. It never get closer to any specific number. So you can see that in this case the limit n goes to infinity, an you can see does not exist. So it does not exist. So that means so the sequence diverges. Yeah, so we use the word diverges, and you can see that it's not gonna go anywhere, but we call, because how we define, if it not converge, we call it diverge. That's how we define it. So that's why we're gonna see something like this. And then I want to do one last example. How about this? So let's look at this situation. So let's say your first number is here, maybe 0, and your second number is there, your third number is here, fourth number is there, fifth number is there, sixth number is there. You can see that it doesn't go too far. You can stuck with a particular value. For example, this value, you can see it does not go away from it. So you can getting closer and closer to that number. So there's a number like that. The numbers are getting closer and closer to this value. So in this situation, you can see that the limit n goes to infinity, an equal whatever the number L is a number, maybe 2 or 3 like that. So you can see, so that means the sequence getting closer and closer to that number. So so the sequence converge. And one extreme situation is this. So maybe this case, so you can see so this is a number, this is your number L, so, and this is a sequence. You can start here and then go there and then go there and then go there. So you can see getting closer and closer to that number again. So those are the numbers. You can see they are getting closer and closer to that L. Okay, so there are situations like that. So if you kind of connect them, you can see well. So this is how it behaves. You can see. So that means in this situation also you can see that the limit n goes to infinity, an equal L. So the sequence converges. Okay, so that's the idea. I hope it's clear now. So the graphical representation makes much easier to understand it. So let's talk about what we mean by diverge. Okay, so diverge to infinity. So now we know what it means by converge or diverge, but there's a term, another one, what we call diverge to infinity. To diverges to infinity. Diverges to infinity. So let's look at an example. How about this one? So if you try to graph an equal n, or in other words n going from 1 to infinity, what it looks like. So you can see that at 1 you get 1, at 2 you get 4, at 3 you get 9. It's not to scale, and at 4 you see that you get 16. This is not to scale because there's a it's going to create a parabola if you look at those points on a parabola. So those are the points. So you can see that those numbers are getting larger and larger every time, but this example is completely different from this example. Let's go back. You can see, remember 1 and negative 1, 1 and negative 1. So it just jump between two numbers. But if you look at this example, it's like it's different here. It's every time it goes, it increases. Every time it increases. So in this case, and then it increases indefinitely. So in this case, we can say the limit when n goes to infinity of an, we say it is infinity. So but we normally say that, so the sequence we know that is diverge, but there's more to it. We say it diverges to infinity. So diverges to infinity. Diverges to infinity. So it's slightly different from previous situation. So we call it diverge to infinity because those numbers are getting infinity. So let's look at one more example. How about this one? So let's say an, I'm going to put a negative one in front. So n times n. So there's a sign change, and also there's a jump. So fluctuate. So let's try to look at the graph in this situation. So how it looks like. So at 1 you're going to get negative 1. Okay. And at 2 you're going to get 2. At 3, what's going on? At 3, so at 1 you get negative 1. At 2 you get 2. At 3 you get negative 3. And at 4 you get 4. At 5 you get negative 5, like that. So you can see that those numbers fluctuate. Every time it's fluctuate, and you're going to get there. So fluctuate. So if you look at the graph, if you connect the dots, you're going to see that like this, down, up, down, go up. So you can see that it's fluctuate, but every time it's getting larger and larger and larger in magnitude. So it's going to jump between those two values, but it's getting larger and larger. So you can see that it does not go with any of them. So it's not converging to any number. It's not getting close and close to any number, but it's not also going to infinity. So it just go to positive infinity and negative infinity, both sides. So in this case, so this is not diverge to infinity situation. In this case, we say just diverge, because the reason is the limit n goes to infinity, an, you cannot say this infinity, it does not exist situations. There's no one side it going to. So you can say that, so diverges. It's gonna diverge. It's a diverge situation. Diverge. Perfect. Now what we're trying to understand, so now we kind of understand what it means by converge and diverge. So now what we want to know is like, how to calculate those limits, because that's the major part. How to calculate the limit of convergence. So so let's talk about that. So calculating limits. Calculating limits. So or algebra. Okay. So we have this nice theorem. So what it says that, so let's say you have two sequences an and bn. So you have two sequences a and bn, two converging sequences. So you have two converging sequences such that the limit of the first one is a and the limit of the second one is b. So then what happened? You can just do this regular algebra. You can sum it, you can add them. So sum. So that means if you look at the new sequence, which is the sum of the two an plus bn. So that means you're going to create a new sequence adding terms of all those like all sequences. So if you try to find the new limit of this one, it is simply the sum of the two, a plus b. So it even works for the minus sign. It even works for the minus. If you subtract, you subtract. And then that's the first one. And then we have the product rule. So that means the limit n goes to infinity a n times b n. If you need what is this sequence going to converge to, it converges to a times b. Very interesting. And then 3 constant multiple. Constant multiple. So that means you have a sequence. What you're going to do, you're going to find a new sequence. How to get it? You multiply each term by k. K is a number. So if you do that, it says that you can just pull the k out. So limit n goes to infinity a n. So in this case k a. So that's the new limit. Number 4, the quotient rule. So what it says that the limit of a n over b n, there's an assumption that the limit the b is not equal to 0. So this is simply a over b if b not equal to 0. If b equal to 0, we can do it like that. We need to kind of study that separately. So it says that you can just do basic algebra. So that means makes those calculations much easier. Okay, because you can just apply the basic algebra. So let's try to find several situations here. So how about these examples? Find the following limits. Find the following limits. Actually, limits of sequences. But because we only study the nth term. So if you study the nth term, you can say everything about the sequence. Okay. So the first one, limit. So what we try to do, we try to see what's going to happen to this sequence, -1 of n sequence. So what's going to happen to this sequence? That's the nth term of a sequence. So but what the theory says that this is a constant multiple. So we're going to pull the multiple out. So it's a limit n goes to infinity 1 over n, and you can see that 1 over n, when n goes to infinity, n getting larger and larger, so it goes to 0. So it is negative times 0. That means 0. So it's a finite number. That means the sequence converges. So if you look at the sequence with the nth term, -1 over n, it's going to converge. So we can say the sequence with nth term 1 over n converges to 0. So we can write it like that. It goes to 0. B, limit n goes to infinity n minus 1 over n. So that's the sequence. So what do you do? Just take the limit. So limit n goes to infinity, and we know that when you handle infinity, is what we normally do. We can divide the top and bottom by the largest term of the denominator, in this case n. So we can divide by n the top and bottom. So you're going to get 1 minus 1 over n when you divide by n, and you can see that this is a very simple limit. When n goes to infinity, 1 over n goes to 0. So this term goes to 0. So you simply end up with so it's simply the limit of n goes to infinity 1, but it's a constant. So actually we can so here there's a difference of the two. So you can write this as if you use the first property, you can break these two limits, and you can see that the second term goes to 0. So that's the kind of best way to understand this one, using the first number 1, result number 1. So this goes to 0. So that means you simply end up getting 1. So it's become 1. So 1 minus 0. So but which is 1. Okay, it's 1 minus 0, but that is 1. Good. So let's look at one more. How about this one's limit? N goes to infinity. 4 minus 7 n to the 6th over n to the 6th plus 3. Again, this is n goes to infinity situation. So what we normally do is we can divide by the largest term. So if we divide by the largest term of the denominator, that's n to the 6th. So if we divide by n to the 6th, it's become 4 over n to the 6th minus 7 over 1 plus 3 over n to the 6th. And you can see that when n goes to infinity, n to the 6th, 1 over n to the 6th goes to 0. So that means you're going to get 0 minus 7 over 1 plus 0. So that means negative 7 is the limit. So that means the sequence with the n term, the sequence with the n term, the sequence with the n term equal to that converges to negative 7. It converges to negative 7. Okay, so let's also study a few other cases. So there's a nice theorem called the sandwich theorem. So let's talk about that. So the theorem is called the sandwich theorem. Sandwich theorem. So let an, bn, and cn be sequences such that an less than or equal bn less than or equal cn. Now if so those terms are in this order, so an is smallest and then bn and then cn, so the an and bn cover bn. So then say if the limit of the outer two, that means if the limit of an exactly equal to the limit of cn equal to a number, some number, then what it says that then the middle one is like a sandwich, then the middle one also has the exact same limit, then the middle one also has the exact same limit. That's what we call the sandwich theorem. So if the outer two goes to a particular limit, the middle one has to go to the same limit. If the outer two goes to one limit, then the middle one has to go to the same limit. That's what's called the sandwich theorem. It's like a sandwich. Okay, so so interesting idea. So it's like a sandwich. So the outer two goes to one place, the middle one also goes to the same place. Well, that's clear because it all goes at the same time. Okay, so let's try to see how we can use this in a practical situation, like in a problem. So so you can see that the we can see that the cosine or n of n goes to 0. Why? Because you know that the cosine is always in between -1 and 1. So what we can do, we can divide all three terms by n. So we divide all three terms by n, then you're going to get -1 over n cosine n over n 1 over n. But you know that when n goes to infinity, it's very clear that this goes to 0, that goes to 0. So by the sandwich theorem, this also has to go to 0. That's by the theorem. Because the outer two goes to 0, so the middle one has to go to 0. So let's look at more examples. B 1 over 2 to the n goes to 0. Why? is very similar. So we know that each term is in between 0 and 2n and 1 over n, because 1 over 2n is smaller than 1 over n because you are raising to power. But we know that these two goes, it's already 0, this also goes to 0. So that means by the sandwich theorem, since the outer 2 goes to 0, 1 over 2n also has to go to 0. Maybe one more. So let's say negative 1n 1 over n. So this also we can look at this one in a similar pattern. You can see that all these numbers are between 1 over n, negative 1 over n, and 1 over n. Is that right? When you have negative 1 to the n, all these numbers are always between negative 1 over n and 1 over n. But we know that these two goes to 0. So this goes to 0, that goes to 0. So that implies that the middle one has to go to 0 as well. Easy to see. Okay, goes to 0. It's very clear because the two corners goes to 0, so that the middle one has to go to 0. Okay, then we have this another theorem. So let's say if the absolute value of a sequence goes to 0, absolute value of the nth term goes to 0, then the sequence has to go to 0. So there are situations it's much easier to consider the absolute sequence compared to the original sequence. So this can help you in such situations. And so for example, let's look at a situation like this. So I'm going to say D. I'm going to say D. So the sequence negative 1n sine squared n plus 1 over n. So if you look at this sequence, so we can check whether this converge or not. But the easiest way to do that is consider the absolute sequence. So if you consider the absolute sequence, what's going to happen? So you can see that. So we have negative 1n. So we can take the absolute value. You can take the absolute value, but this sequence is bounded by what? In this side it is bounded by 0 because when you take the absolute is always greater than or equal. And then here what's going to happen? You can see that sign is always in between negative 1 and 1. So it doesn't matter what you have here. So it's always in between 1 and negative 1. But in this case, since it's square, it's a 0 now because you square it. So it's not negative 1 anymore. It's 0. So it's between 0 and 1. Now what we can do, we can divide everything by n, so it's less than n. So now it's very clear in this situation. It's very clear in this situation. This is automatically 0, and this also goes to 0. So by the sandwich theorem, the absolute sequence goes to 0, but the theorem says that if the absolute sequence goes to 0, the original sequence goes to 0. So that means this implies that the original sequence goes to 0 as well. So that's the easiest way to prove this one. You consider the absolute sequence instead, and then you can show that it's gonna goes to 0. Okay. So let's try to do maybe one last one before we move on to the next result. So how about this? For example, find the limit n goes to infinity n plus 1 over n square root, something like that. So what do you do? You can take the limit inside. So we have limit. We can take the limit inside. N plus 1 over n square root. So you bring the limit inside. That's what they did. So this is a kind of common trick that we use. And then you can see that this simplifies very well. This is an infinity situation, so that means the limit we can divide by top and bottom. So it's a 1 plus 1 over n square root, and you can see that this term goes to 0. So that means you're gonna get 1 under square root, so it's 1. So that means the sequence converges to, if you look at this as a sequence, if this is the nth term, the sequence gonna converge to 1. So here, so you can see that this is a kind of general pattern. So what we're trying to do is we kind of identify a continuous function here. So so in this case, what's the continuous function? We're gonna consider the square root function. So and then what we do is, so when you look at the square root function, the graph of the square root function looks like this. So what's gonna happen, instead of the sequence, you look at the corresponding function here. So the corresponding function is square root x, and what's gonna happen, you can see that inside it goes to 1. So you pretty much calculate the value at 1. So that's the limit is going to converge to. That's why you get 1 here, because the inside goes to 1, so outside goes to 1 as well. So but this is a nice theorem. So let's try the general theorem here, because it's very useful. So it's called the continuous function theorem. Continuous function theorem. Continuous function theorem. So what it says that let we can say let an be a sequence. Let an, so it's not clear, so I will rewrite it. Let an be a sequence. Let n be a sequence, and and the an is given by fn. So you have a function. When you plug in n, you get an. Okay. So let n be a sequence, and an is given by a function by plugging n. With f is continuous, and the limit of actually so I'm going to kind of slightly change the wording of this problem. Yeah, so let's slightly change the wording of this problem. Yeah, so you can write this problem theorem in a different way. So let's write this version, it's much easier. So let's say be a sequence, such that the an goes to L. An goes to L, and f is continuous. So you have a sequence. That sequence converges to L. A sequence converges to L, but f is a continuous function. F is continuous at L, at least at L. Then what it says that then the f of an. So that means if you plug in that values into the if we plug in the sequence into the function, it says that this gonna also gonna converge to f of L. So that's the kind of result that we used earlier, because you can see that inside the function goes to 1. So the outside, what is gonna happen, you're gonna simply plug in that value to L. So that is, so in short, we can remember this one because this is what we use in problems. It says that you can bring the limit inside. So limit n goes to infinity, f of an equal f of limit n goes to infinity an. So what you do is you're going to bring the limit inside. Okay, so this is simply f of L in this case. So that's the theorem. You can bring the limit inside. So remember, this is like very powerful result. We use this a lot. So this is very helpful. And then so this happens if f is continuous, if f is continuous at L is the limit of the inside of the sequence. So what you can do is you can bring the limit inside if the function is continuous. If the function is continuous, you can bring the limit inside. So let's do like a kind of different example. Okay, so let's say example, find the limit of the sequence, find the limit of the sequence find the limit of the sequence, or in other words, I'm asking whether the sequence converges or not. Okay, find the limit of the sequence given by an equal, let's say tan inverse 3 pi n squared plus 4n over 1 plus 3 pi n squared, something like that, you know. So find the limit of the sequence given by an equal tan inverse 3 pi n squared plus 4n over 1 plus 3 pi n squared. So what we're trying to do is we can identify a function that is continuous, and then we can bring the limit inside. So what we're trying to do, so the answer, since y, so what's the function? Function is tan inverse. See that? Tan inverse x is continuous. Since y equal tan inverse x is continuous, we can take the limit. So what is the shape of tan inverse x? So tan inverse x has a special graph. This is useful most of the time. We used this earlier also. So tan inverse has two asymptotes. It's going to go between negative pi by 2 to positive pi by 2. So this is pi by 2 and this is negative pi by 2. So it's in between positive and negative pi by 2. This is infinity, this is negative infinity. So this is the graph of tan inverse x. This is very useful in most of the situation, but you can see that it's continuous everywhere. It's a nice continuous function. So you can bring the limit inside in this situation. So that means, according to the previous theorem, the continuous function theorem, if the function is continuous, you can bring the limit inside. Okay, function is continuous, then bring the limit inside. So we're gonna do that. So let's bring the limit inside. So the limit n goes to infinity, an is simply limit n goes to infinity, tan inverse 3 pi n squared plus 4n over 1 plus 3 pi n squared. So what we can do, we're going to bring the limit inside. So tan inverse, if you bring the limit inside, the limit n goes to infinity, 3 pi n squared plus 4n over 1 plus 3 pi n squared. Now this is a regular n goes to infinity situation. So what we do, we can divide by the largest term, the top and bottom. So that means n squared, we can divide by n squared, top and bottom. So it's a limit n goes to infinity. If you divide by n squared, you're going to get 3 pi plus 4 over n, 1 over n squared, 3 pi. That's what you get. Okay. So you can see that this term goes to 0 and that term goes to 0. So those two goes to 0. So that means you simply end up getting what do you get? You simply end up getting tan inverse. You're gonna get 3 pi or 3 pi. So it's a limit n goes to infinity, 3 pi over 3 pi, and you can see 3 pi get cancelled, so this is simply 1. So that means you're gonna get tan inverse 1. Tan inverse 1 is pi over 4. So the sequence converges to pi over 4. So you can see that how the math works here. So it's very simple, and you can see that it's end up with pi over 4. Okay, interesting example. Okay, so there's another version of that theorem. So let's look at this version. So it's like very similar but slightly different. So what it says, suppose a sequence an is, suppose n is a sequence defined by is a sequence defined by an is simply fn. So when you plug in n, you're going to get an. So suppose an is a sequence defined by n equal fn. Now it says that if the limit of the sequence when n goes to infinity is the limit of the function, if the limit of the function is L, is automatically says that then the limit of the sequence also has to be L. So this is a very interesting one. So you kind of look at the corresponding function. That's what it says. Just look at the corresponding function. That function tells you what's going to happen to the sequence. So this is a very powerful result. So I'm going to put a star here because we use this a lot. We use this a lot. Okay, so I'm going to put a star here. So this is one of the most common results. So what it says that your sequence is defined by a function, but the function goes to a particular number when x is not n here, is x. So there's a so what you can do is just put one letter in both places. So so this is, you can say n, this can be n. Okay, so so what it says that, so the sequence is defined, there's a sequence which is defined by a function, but the function goes to finite value when n goes to infinity, then the sequence also goes to that value. Actually this L can be infinity. So so graphically this is very easy to understand. So let's say this is your function, and then what you're going to do, you're going to pick at a particular value. So when you pick at 1, that's the a1. When you pick it up at 2, that's a2. when you pick it up at 3, that is A3, 4, A4, like that. So that's how you get the terms of the sequence. So that's the idea. So because you have a general function y equal fx that has its own behavior, but what we can do, we can evaluate at particular values. We can evaluate at 1, evaluate at 2, evaluate at 3, evaluate at 4, like that. So once you evaluate at those points, it's going to give you the sequence. So you can see that it's going to generate the sequence A1, A2, A3. Those are just values. So what it says that the sequence follow this pattern of the function. The sequence follow the pattern of the function. Okay, so that's the idea. So whatever happened to the function, the same thing will happen to the sequence. So let's look at several cases of this one. Actually, I'm going to do one example, and then we're going to go to one of the very important result. So let's look at this example. So find the limit of the sequence. Find the limit, or test whether it converge. Okay, find the limit of the sequence given by an equal ln n over n. Okay, find the limit of the sequence given by ln n over n. So you can see that when n goes to infinity, ln n over n both goes to infinity. So that means we can use the L'Hopital's rule in this situation. So we can use L'Hopital's rule. Okay, so you learn L'Hopital's rule in Calc 1. So now we're gonna use the L'Hopital's rule for this situation. Okay, so this is one of the application of that. So how to do it? Let's try to finish the problem. So so what we normally do is you can replace n by x. That's how we start it. We can replace n by x. So the answer, the corresponding, so what we try to do, we can try to find a corresponding function. It's very easy to get the corresponding function. We can replace n by x. Okay, so we can look at the corresponding function. So the corresponding function is fx equal, what is the corresponding function? It is ln corresponding function is ln n over n. That's the corresponding function. No, I'm sorry, it's not the, it's x, because you replace x by n. So the corresponding function ln x over x, that's the corresponding function. Now what we try to do, we're going to find the limit of this one. So the limit n goes to infinity fx. So what we try to do, we're going to find the limit of this function. Limit okay, actually, because the variable is not n, variable is x. So x, so limit x goes to infinity ln x over x, and then we can use the L'Hopital's rule here. So we can take the derivatives. So it's the limit x goes to infinity. Derivative of the top one is 1 over x, the bottom one is 1. And you can see that so this is simply limit x goes to infinity 1 over x. So 1 over x means it is 0. So the limit is 0. So that means so the corresponding function goes to 0. So therefore the limit has to go to 0 due to the previous theorem. The previous theorem says that whatever happened to the function, so the same thing will happen to the sequence. As I says, it says whatever happened to the function, the same thing will happen to the sequence, same limit. So we can use that idea. So we just simply look at the corresponding function. So according to that theorem, so therefore the limit of the sequence is also 0. So it goes to 0 because the corresponding function has a 0 limit. So therefore the sequence should also have a 0 limit. So this is an important example. So here we use the L'Hopital's rule to find the limit. Okay, and then we have one of the very important set of results. So I'm going to write this result and do maybe one example from that. So let's try this theorem. Okay, and this is not in the book, unfortunately. So the theorem is I'm going to say following limits are important. Following limits are important. Following limits are important. So we're going to say FLI, fly. Okay. So what are these? The first one is the result that we just proved. So the limit when n goes to infinity, ln n over n, this is equal to 0. We just proved that it is equal to 0. That's the first result. The second result, the limit n goes to infinity, xn equals 0 if the absolute value of x is smaller than 1. So limit of xn equals 0 if the absolute value is less than 1. And number 3, the limit of n goes to infinity, x to the 1 over n. You try to find the nth root. If you find the nth root of x, it is 1 if x is positive. It's a very important result. So if you pick any positive number and if you try to find the nth root, it is 1. And number 4, the limit n goes to infinity, nth root of n is also 1. So if when n goes to infinity, if you try to find the nth root of n, it is 1. If it that's one result. But if you try to find the nth root of x for any positive, it's also 1. So 2 different problems. Number 5, the limit n goes to infinity, x to the n over factorial n. So what does factorial n means? Factorial n means, like factorial 3 means, called factorial. It's 3 times 2 times 1. You're going to multiply all the numbers up to 1. So when you say factorial n, it means n and then n minus 1, like that, 3, 2, 1. That's factorial. So if you have this number, for any n, it is 0. Okay, for any x, can be positive, negative, any large number, but it says that if you have xn over factorial n, which is equal to 0. And the last one is the limit n goes to infinity, 1 plus x over n to the nth power. See where you see n? This 1 plus x over n to the nth power. 1 plus x over n to the nth power. And it's very interesting. It's going to go to e to the x. This is ex. This is another definition of ex. Okay, so I'm going to put a it's like slightly different. So yeah, so those 6 results, these 6 results are very important, and make sure that you remember them. We can use this a lot in several situations, but unfortunately this is not in the book. So yeah, and also I want to add one more result here. If you have factorial 0, that's an important result. It is actually 1. So factorial 0 is 1, so that you need to remember. Okay, so these 6 results are important, and then we can do some problems from that. Quick examples. So so let's do a problem like this. So I'm going to start with a little difficult one first, and then do easy ones next. So how about this? So example, does the sequence whose nth term is an equal n minus 2 over n converge. Or n to the n converge. That's the sequence whose nth term is an equal n minus 2 over n to the n, n minus 2 over n to the n converge. So let's see how we can kind of answer this kind of question. So what we try to do, we try to use one of those results there, and you can see that if you look at those results, the 6th one is like kind of very close to this. The 6th one is very close, so I'm going to use the 6th one here. So let's start with an. So the answer, let's start with an. So n is n minus 2 over n to the nth power. So what we're trying to do, we're going to try to bring this to this form. We're going to try to bring this to this form. That means we write 1 plus or minus something. That's how we're trying to do. And whatever x you get is going to go there. So let's see. So so you can see that you can write divide by 1, divide by n. So you're going to get 1 minus 2 over n to the n. Right? So that is of the exact same format that we have. So that means according to that theorem, this going to converge to, as n goes to infinity, e to the, here x is similar to what? See, x is that term. So if you take out that, so x is that term there, sitting there. That means in this case x is negative 2. So this part is x. That means it is e to the negative 2. That means 1 over e squared is converged to 1 over e squared. Okay. So this sequence can converge to 1 over e squared. So that's the answer. It's 1 over e squared. Good. Okay, so I'm going to give you a extra credit problem for you to try. So you can try this problem. So does the sequence with an equal n plus 1 over n minus 1 to the n converge? So actually we did not finish the problem earlier. So you can see this finite, so converge. So we have to finish the problem. So you can see that there's a finite number, not less than 0, it's infinity. So it's a finite number. That means we write less than infinity means finite. So it's finite number. So the sequence converge. The sequence converge. Okay, so less than infinity, or it's finite. So the sequence converge. Good. Okay, so you can try this problem. So let's do a few more examples before we finish this part. So find the limits. Find the limits. So A, ln n squared over n. B, n squared n. C, 3n n. D, negative 1 over 1/2 n. And E, 100 n over n factorial. Okay, let's try to do this. So we have easy ones. So so according to this theorem, you can see that x to the n of factorial goes to 0 for any x, and then also xn goes to 0 when the absolute value of x is less than 1. So we can use that to answer some of the questions now. So you can see that this gonna go to 0 since the absolute value of this is less than 1. This also goes to 0 where x equal 100. It's just a number. Okay, so this both goes to 0. Okay, and then the other ones we need to kind of simplify. So we can take 2 out. So we take 2 out. So 2 ln n over n. But we know that ln n goes to 0. So this goes to 0 as n goes to infinity. And we need to simplify this one a little bit. So this is n squared 1 over n. So now what we can do, we can write this one as 2 not 2 can write this one as n 2 times 1 over n. Now you can switch the power, so we can say n 1 over n squared. So we switch the powers. You see that? Switch the order. Now we can see that this part goes to 1, so that means goes to 1 squared as n goes to infinity, but 1 squared is 1. Okay, so this is equals to 1. That means this can convert to 1. The same thing here. We can split this, so this is 3n to the 1 over n. So that means it is 3 1 over n, n 1 over n, and we, from the previous result, we know that this both goes to 1, not equal. Actually, you can say equal, convert. You can say goes to 1 as, so this is equal to 1. As n goes to infinity. Okay, so that's what happened here. So you can see that you're going to converge to that. Okay, and then the last like quick topics we have what we call the recursive definition. Let's try to talk about that. The recursive definition. Of a sequence. So what we can do, so find the sequence given by, find the sequence given by, find the sequence given by a1 equal 1, an plus 1 equal an plus 1, where n greater than or equal to 1. So what's going to happen? So this is what we call a recursive definition. It's kind of explain how to get the next number. So you just need to plug in. So for example, so let's try to find the other numbers. So we have a1 equal 1, a2. So how to find a2? According to the formula, it says that a2, that means when you plug in 1, if you plug in 1 in the second one, it says that a2 equal a1 plus 1. But a1 is 1, so it's a 1 plus 1, so that means 2. So that's the second term. Now if you want to find a3, according to the formula, it is a2 plus 1, because to get a3 you're going to plug n equal 2 here. So but a2 we already know it is 2, so 2 plus 1, so it is 3. So this is what we call the recursive definition. So likewise we can calculate all the other terms. Okay, it's called a recursive definition. So there's an interesting function given as a recursive definition, is what we call the Fibonacci sequence. Fibonacci sequence is like a interesting situation. Fibonacci sequence. So it is given by a1 equal 1, and then a2 equal 1, so they're going to go two terms, and an plus 1. The next term is simply given by the sum of the previous two. So an minus 1, n start with 2. So this is what we call the Fibonacci sequence. a1 equal 1, a2 equal 1, an plus 1 equal an plus an minus 1. So let's try to use this to find the first few values. So so a1 equal 1, a2 equal 1, a3. To get a3 you want to plug in n equal 2. So if you plug in n equal 2, you're going to get a2 plus a1. If you plug n equal 2, that's what you get, a3 equal a2 plus a1 according to the formula when you plug in n equal 2. So now you can calculate them. a1 equal 1, a2 equal 1, so you're going to get 2. That's the a3. What is a4? a4 is, now you need to plug in n equal 3. If you plug in n equal 3, you get a4. So that means a4 is a3 plus a2. So a3 is 2, and then plus a2 is 1, so you get 3. So just you can find, so then a5, so it is a4 plus a3. You just add the previous two, so it is 3 plus 2, so it's 5. So you can do it. Okay, so there are several interesting results of this sequence. So this is a sequence like, it's everywhere pretty much. This is in engineering, it is in physics, it is in mathematics, it is in computer science. So one of the important results is, if you look at the limit when n goes to infinity, an plus 1 over an, you divide two consecutive terms and see, we can look at the ratio of those two, and you can show that it is simply 1.618, like that. And then this is like very important number in mathematics. This is normally we denote by phi. This is what we call the golden ratio. So this is called the golden ratio. golden ratio. This number is called the golden ratio, and this golden ratio is like kind of appear everywhere in nature. So there are a lot of situations where you're gonna see this number. So one of the interesting situation is if you want to find kind of create a nice envelope that someone is pleasing with that. So what you want to do is, if you want to find, if you know the length and the width of this ratio, if you keep exactly the length and the width in this ratio, it is known that most of the people like that if you have this ratio to the length and the width. So this so if you kind of create an envelope with that ratio that has the golden ratio, and so that's one of the pleasing one. Okay, so this is just one situation. This everywhere. It appears in flowers, it appears in seashells, so there are a lot of situations. Okay, so that's the one, and then we're going to go to the last topic of this one, is the bounded sequences. So let's try to talk about that, and that's the end of the sections. You can see this is a long section because a lot of things to discuss. Okay, so bounded sequence, bounded sequences. So so let's talk about the idea. So the definition. So if all the terms of the sequence is, so if n is less than or equal m for all n, we say the sequence n is bounded above if m less than or equal n for all n, we say n is bounded below, bounded above and bounded below. So if you can find a larger number which is larger than all the terms of the sequence, we say it is bounded above. And if you can find a smaller number which is smaller than all the terms in the sequence, we say it is bounded below. And if a sequence is both bounded above and below, we say it is bounded. Okay, so look at an example. So the sequence -1 to the n is bounded since the sequence, the numbers, those are the numbers you get, is less than or equal 1, and on this side is -1. It's between -1 and 1. So you can see that that's the small m, that's the large m, so it's bounded. Okay, so you can find a larger number and a smaller number that covers the sequence, then it's bounded. Okay, and then we have the monotone sequences. So another definition. A sequence is monotonically increasing, monotonically monotonically increasing in some books is called non-decreasing. Non-decreasing. Monotonically increase, some people call it non-decreasing if an is less than or equal an plus 1. So the next number is either equal or more. It's called monotonically increasing, and it is monotonically decreasing monotonically decreasing if an is greater than or equal an plus 1. So it's going down, either equal or less. Monotonically decreasing, or we call this is also non-increasing. Okay, that's a different name. Yeah, so it's a monotonically increasing, that means getting large, either equal or more. Monotonically decreasing means equal or less. And then there's a theorem. So it says that, so let's try, that's the last result. And then okay, no, so we just need to finish something. So a sequence is monotone if it is monotonically increasing or monotonically decreasing. A sequence is monotone if it is monotonically increasing, or decreasing. Okay, if it's either monotonically increasing or decreasing, we call the sequence is monotone. So then we have this interesting theorem. So what it says that if the sequence is bounded and monotone, it has to converge. So if a sequence is both bounded and monotone, if a sequence is both bounded and monotone, then it converges. Okay, so it says that if we have a sequence which is both bounded, it's a bounded sequence, there's a two number that covers, and also monotone, either one of them, either monotonically increasing or monotonically decreasing, one of them, then it has to converge. Okay, so a nice example would be something like this. So example, we're gonna say sequence a n equal, let's say 3 minus 1 of n converges, because it is bounded, and also you can see this monotone is monotonically increasing, because every time what you subtract getting smaller, so the numbers getting larger. So that means if you look at the graph, this is how it looks like. So the graph gonna look like that, as gonna converge to 3. Okay, so yeah, so this is what we call the monotone convergence theorem. Monotone convergence theorem, it's just a name, it's called monotone convergence theorem. Monotone convergence theorem. Monotone convergence theorem. According to the theorem, it says that if a sequence is both monotone and bounded, then the sequence has to converge, okay, by the monotone bounded theorem or monotone convergence theorem. Okay, so this is the end of the sequence section, and you can see that this is a kind of large section because there are a lot of things to discuss. So at least try to go over this twice so that all the topics are kind of very clear, because we're going to use this idea again and again in the next several sections. Thank you.